And welcome to today's session for Physical Sciences. My name is Tem Ngube. This session is proudly brought to you by the Department of Free State Education, the Department of Education, Free State, in collaboration with Parama Research and Development. So it is Physical Sciences today. We are focusing our attention on the paper 1 section on electricity and magnetism, which we will try and zoom into electrodynamics, which is electromagnetism. Right. So without any waste of time, let's look at the breakdown in terms of where does the section on electrodynamic fall, or what weight does it contribute to the paper 1. Right. Okay, if you look at the weighting of the prescribed content, we are talking electricity and magnetism, which is a total of 55 marks. So the 55 marks has to do with question 7, which is purely based on electrostatics, right? Which talks about charges at rest. And then we've got question 8, which focuses on electric circuits or electricity, right? Of which the circuit are a main component thereof. And then question 9 of paper 1, which focuses on electrodynamics, right? So we are on question 9. So if you add the total for the 3 questions in the long section, obviously there is the multiple choice, which covers the entire spectrum of all the topics that fall within the physics section, right? So if you add all the marks from section A, which is multiple choice, question 7, which has to do with electrostatics, question 8, which has to do with electric circuits, as well as electrodynamics, you get a total of 55 marks. So if you compare the 55 to the 65, I think this section is the second largest weighting in terms of the physics paper, right? So of this, we are saying the 55 marks, but we're focusing our attention on electrodynamics, right? Now let's look at the concept map as to how the electrodynamics is actually laid out, right? So electrodynamics speaks to principles. In this case, we are talking about Lenz's law, right? Which talks about the induction of electricity or current or EMF, the Faraday's law, which talks about the mathematical relation and explains the Lenz's law. We've got the Faraday's law, okay, right? And then we've got motors and generators. So these the components, or rather the electrical machines that we speak of. So we've got motors and generators, and each one of them has got both an AC and a DC, right? And then we also speaks to the alternating current, right, which has to do with graph. And then we also talk about the root mean square voltage, which has to do with the alternating current. So this focuses on the alternating current precisely, right? And then we'll talk about the data sheet with respect to the problems and the equations. So the data sheet or the formula sheet is a very important component of electrodynamics, right? Having said that, let's look at the content progression. What is it that we know by now, and what content did we do before we arrived at this topic in grade 10 and grade 11? That is very, very important for us to actually lay the foundation for the concepts that we're going to discuss today. Right, in grade 10, we spoke of magnetic fields, right? Where we appreciated that we've got a magnet, and a magnet is a dipole. It consists of the north and the south pole, right? Now, and then we appreciated that around the magnet, there is what we call a magnetic field, right? So the field is around the magnet, like that, okay? Like that, right? And the direction, because in the field, a magnetic material will experience a force, then the field has a direction north to south. So it's from the north, okay, to the south, like that. So this is a typical example of a magnetic field. And what exactly makes a material to be magnetic? It must contain the three ferromagnetic elements, right? Ferromagnetic elements, okay? So if it is an element, we're talking about a substance that we can find or we can locate in the periodic table of elements. The first one is the ferrous metal, which is iron, okay? It is a ferromagnetic element. We've got nickel as well as cobalt, right? So these three elements, they contribute in a material having or possessing magnetic properties, right? So this is what we know from grade 10. And then we know that like poles, they repel, and unlike or opposite poles, they attract. So that's as far as we went with grade 10. And then in grade 11, we discussed a magnetic field around a current carrying conductor. And then we spoke about the Faraday's law, which talks about the relationship between induced EMF and the rate of change of magnetic flux using the equation E is equals to negative N delta change in magnetic flux linkage, and then we spoke of the rate. So the Faraday's law can be presented as an equation, but at this stage, we're not so much interested in the equation itself. What is of particular interest to us is how do we induce EMF? How do we actually induce current across the ends of a conductor? Right. And then in grade 12, we're focusing our attention on electrical machines, which is your generators and motors. So for the purpose of today, we will zoom our attention into the detail of the functioning, the components, the applications or uses of these different types of electrical machines that we shall take a discussion on. Right. And then in our follow-up lesson, in anticipation, next week, in our live session, we'll look at alternating current, which is, to some extent, it's a standalone subsection of electrodynamics. So for today, we're looking at electrical machines. That's the core focus for today. Right. Moving forward. So in grade 10, we've already indicated that a magnet is a dipole. So the word di means two. So when we say a magnet is a dipole, it simply means that it consists of two opposite poles, right? So a magnet is always a dipole. So it means if we had got we have a magnet like that, we've got the north and the south. Suppose we break that magnet into very small pieces. It has been proven that the magnet always exists as a dipole. So we can't have the North Pole existing in isolation or the South Pole existing in isolation. Right. So a magnet is always a dipole. It consists of two opposite poles. Right. And then now around the magnet, we've appreciated the fact that there is a magnetic field. So in a magnetic field, if you subject or put another magnetic material around in a magnetic field, it will experience a non-contact magnetic force, right? So the field is invisible. So the magnetic field is invisible, okay? You can't see the field, but we can see the effect of the field because in that field, there is a force, right? So it is invisible. So we use the imaginary lines, okay, to represent the magnetic field, right? And then the direction of the field is north to south. So the ion filings that have been scattered in this case are, and then two opposite poles have been put at some distance apart. This shows the field pattern that exists between these two opposite poles. And remember, the direction of the field is north to south, north to south. And then we've got that, okay, got that. So I'm merely tracing the field using the ion filings there. So this is a demonstration that around a bar magnet there exists a magnetic field. So this is what we know in as far as grade 10 work is concerned. All right. Okay. Now in grade 11, fast forward, we looked at the Faraday's law. Now let's remember the equation for Faraday's law states that it's written E is equals to negative N delta phi, okay, over delta T. Right. So this is the Faraday's law. Okay. But what does it say? It talks about the relationship that exists between the magnitude of induced EMF and the rate of change of magnetic flux linkage. So when we talk about rate of change of magnetic flux linkage, we're talking about delta phi over delta T. So this represents the rate of change of magnetic flux linkage. So in other words, the law states or suggests, puts it to us that the rate, the magnitude of the induced EMF is directly proportional to the rate of change of magnetic flux linkage. Now, what that simply means is for us to induce EMF so that this light bulb can glow, okay, let's think of that light bulb glowing. The magnet has to be moved in and out of that coil. So as the coil cuts across these invisible magnetic field lines, EMF is induced across the ends of this conductor. And the moment we have induced EMF, then we have got induced current. That's when the light bulb is going to glow. So by merely moving the magnet in and out of that coil, we are actually changing the magnetic flux linkage. How fast we change the magnetic flux linkage also determines how bright the light is. So it means if we have a greater rate of change of magnetic flux, what does that mean exactly? Let's break it down. So the field is around the magnet. So if that is your magnet and then you put it into the coil and remove it very quickly. So what is actually happening? There is some interaction between the conductor and the magnetic field. Okay? So if the magnetic field is disturbed, that's what we call by changing the magnetic flux. So the rate at which the coil, the magnet moves in and out of the what you call the coil, it will determine how much induced EMF we have. So the greater the rate of movement of the magnet relative to the coil, the greater the magnitude of the induced EMF, and correspondingly, the greater the current. The more the current, the brighter the light bulb. So in essence, the Faraday's law explains to us exactly what happens to the magnitude of the induced EMF in relation or in terms of the rate of change of magnetic flux. So a greater rate of change of magnetic flux correspondingly produces a greater magnitude of induced EMF. So that's what basically the Faraday's law puts to us. Right. So by at this stage in grade 12, we're not required to carry out any calculations using the Faraday's law equation. But we are required, however, to be able to state that relationship. So when it comes to basic recall questions, the question will say, state the Faraday's law of electromagnetic induction in words. So when they say in words, you're not going to write that equation because that's a mathematical representation of the relationship. Right. So that's as far as the law of electromagnetic induction. Right. So also in grade 11, we looked at factors affecting the magnitude of induced EMF. Right. So we've got a magnet, and then we've got a singleton of a conducting material is called a loop. Right. So if we've got multiple turns like this, then this is a coil. So a coil consists of multiple loops. So the higher the number of windings, okay, the higher the number of windings or turns, the greater the magnitude of induced EMF. So when we look at the factors, we're actually asking ourselves, what is it that we can do differently as far as the Faraday's law is concerned for us to induce a correspondingly greater magnitude of induced EMF and induced current? Right. Okay. And then again in grade 11, we agreed, or we actually came to a discovery that if you have got a current carrying conductor, So a current carrying conductor is basically a conductor through which there is current. So if we connect an ammeter at a point here, okay, there is the conductor. Current is flowing. That ammeter is going to register some readings, okay, of how much current we have or how much charge passes through that point per unit time, right? So the rule of thumb, this is the Fleming's right hand rule, okay? What you do, you grab the conductor using your right hand, right? And then the thumb points in the direction of current, right? While the curved fingers points in the direction of the magnetic field. So B represents the direction, the magnetic field. And remember, the magnetic field has a direction. Why? Because in a magnetic field, a magnetic material will experience a force. So if we subject a magnetic material to a magnetic field, it experiences a force, and the force is a vector. So the direction of the curved fingers is an indication of the direction of the field. So B stands for magnetic field, okay, which has got what? A direction. So this is Fleming's rule of thumb. Okay, Fleming's rule, right? And it's the right hand, okay? Right. And then I is the direction of current as indicated in that arrow there, right? So you cannot separate electricity and magnetism. Okay, come to think of it. Electromagnetism is the study of electricity and magnetism because these two are inseparable. Wherever there is electricity, there is a magnetic field. So a magnetic field exists around a conductor that conveys or has current through it. So this is what we learned in grade 11 as part of our foundational knowledge, right? Okay, and then let's look at the factors that affect the magnitude of induced EMF. Okay, in grade 11 we said E is equals to negative N delta phi, okay, over delta T. Okay, so if we are to induce EMF, let's say we had a coil which can spin around an axis. So what that simply means is the faster we spin that coil in a magnetic field, so the speed is a factor because it speaks to the rate. Okay, it speaks to the rate. So the rate at which we move the coil, the magnet into and out of that coil will also impact on the magnitude of the induced EMF. So the speed of rotation of the coil or the conductor in a magnetic field has an impact on the magnitude of induced EMF. That's number one. Number two, we are also saying if we use, let's say we've got a bar magnet, okay, there is a bar magnet, north, south, okay, north, south, right? And then we've got another magnet, right? North, south. A magnet that is stronger is the type of magnet that will have a stronger magnetic field around it. So the strength of magnet has nothing to do with the size, right? So we are going to use a stronger magnet, okay, to create a stronger field, okay, a stronger magnet. So if a magnet is stronger, it means it has got a stronger field, right? So if you move a conductor across a stronger field, there's more induced EMF and more induced current. If you move the same magnet at the same rate through a weaker magnet, which has a weaker field, there will be lesser induced EMF. So the strength of the magnet is also a factor that also affects the magnitude of induced EMF and induced current. For us to have induced current, we must have induced EMF, right? So this is about strength, not size. I must indicate that, not size. So size doesn't matter in this case, right? And then number three, we talk about the number of turns, okay? Number of turns in the coil, okay? The greater the number of turns, the greater the magnitude of induced EMF and induced current, right? Okay, now having looked at the factors that affect the magnitude of induced EMF, let's look at a practical example to demonstrate our understanding. We'll take this as a discussion. Okay, there's a graph R in the diagram which represents the output of an AC generator. Okay, let's think about a generator without zooming our attention into whether it's an AC or DC. Doesn't matter. Now, the alternating current that is output from an AC generator actually changes direction, right? So, according to graph R, there's half revolution and then one full revolution, okay? And then for graph S, it's only half a cycle or half turn of the coil in the magnetic field, right? So the induced EMF is on the vertical axis and time is on the horizontal axis. So the time taken to complete one single cycle or one single revolution is the period. So this is T. So the period of graph R is T. And then the period of graph S is 2T, because this is only half for graph S. This is only half a turn, which is 180 degrees. Okay, so for graph R is 0, that's 90 degrees, that's 180 degrees, half, okay, that's 270, and then that's 360. All right, now it says which one of the following changes has been made to the generator to produce graph S. Now, if you look at the magnitude of induced EMF for graph R, is 40 volts, right? It's also 40 volts. The minus suggests that it's in the opposite direction, but the magnitude is actually equal, right? And then we moved from 40 to 20. So what did we do? Did we increase, decrease the magnitude of induced EMF? So the initial EMF, okay, let's say EMF initial is equals to 40 volts, okay? And then EMF final is equals to half that, which is 20 volts. Did we increase, decrease, or did not change the magnitude of induced EMF? This was a decrease. So whatever we did, it must speak to the three factors that we have discussed. Did we increase or decrease the speed? It's a possibility that the speed was decreased. Number two, did we use stronger or weaker magnets? Possibilities that we might have used weaker magnets because we halved the output in terms of the induced EMF from 40 volts to 20 volts, right? Okay. Another possibility is that we might have halved the number of turns while using the same strength of magnet at the same speed. Okay, and then let's look at each option and decide whether it is true or false, and then we can eliminate. A says the strength of the magnetic field has been halved. This is a possibility. If we have the strength, it means we have the output. Okay, let's look at other options. The surface area of the coil has been halved. So according to the three factors that we discussed, none of these three factors speak to the area. So option B is actually a distract. Okay? And then let's go to C. The number of turns have been halved. Okay? That's another possibility. Okay? And then the other one says the speed of rotation of the coil has been halved. Okay? This is another possibility. Now, we don't know whether half the strength halves the output. However, if you look at the period for graph R is equals to T, and then the period for graph S is equals to half T, and the period suggests that we take so much time, T seconds, for us to produce one complete cycle for R. And then we would actually take double the time, or we only make half a turn in the same time. So the most correct answer is that the speed of rotation has been halved, because the speed speaks to the frequency, it speaks to the rate. Right. So the most correct option there is option D. Right. I hope it makes sense. Right. Moving along. In grade 11, we spoke about the magnetic field around the current carrying conductor. Now let's look at a typical um, electrical machine where a generator where we induce EMF. Right. So if that coil, which is brown in color, spins about that axis, around that axis, what is happening? It is cutting across the magnetic field, okay, or these imaginary field lines. So as it cuts across the magnetic field lines, EMF is induced. That's why the light bulb glows, right? So the rate at which the coil rotates, hence we talk about the speed of rotation. Okay. Now at a higher speed, we induce greater EMF. Okay. Okay, let me go back. Right? And then this has to do with the spinning, whether clockwise or counterclockwise. So speed, the turning, the direction can either be what? Clockwise or counterclockwise or anti-clockwise. Right? So what do we know? We know that the field exists between a pair of magnets. In this case, the direction of field is north to south, north to south, north to south. Okay? And also the field is strongest at the poles. Right. So this is a typical example of demonstrating electromagnetic induction before we actually look at the different types of electrical machines. Right. Okay, what do we have here? We've got an AC and a DC generator. Right. Now, let's agree. For a generator, to determine the force, which is the force has to do with the rotation, okay? Either clockwise or anti-clockwise, okay? The field is north to south. Okay, the direction of induced current is shown by the middle finger, and each one of them, these are actually perpendicular. We actually put them perpendicular to each other, right? So this is a drawing in 2 dimensions. So in other words, we use the right hand rule. So the thumb points in the direction of the force of rotating the coil in a magnetic field, and then this other finger, the first finger, we call it the first finger, it points in the direction of the field, north to south. If I'm pointing like this, it means the orientation is that this side, we've got the North Pole, and then this side, the South Pole. So it's in the direction of the field, which is due to the permanent magnets from north to south. And then the middle finger, that's pointing towards me, in this case, points in the direction of current. And then I can also do it like this, okay? There is the force, okay, lifting up a side of the coil. That's the direction of the field, north to south, and then this is the direction of current, right? So we use the Fleming's right-hand rule to determine the direction of current, the direction of rotation, as well as the direction of the field. So the field in this case is north to south in that direction, right? So this is my field, okay, north to south. So if this is rotating, say for argument's sake, the side on the side BC, what is actually happening? If the side CD, this is CD, right? This is CD, okay? If CD is rotating upwards, and then AB must go downwards because it's a rotation, so its opposite forces are on two opposite sides, so that the direction of rotation is kept the same. So I've got north to south, and then CD is pushed upwards by a force, okay? And then the current moves in the direction of C to D. And then if it's from C to D, it means on the other side is from A to B, all right? So this is a typical example of how we apply the Fleming's right-hand rule, okay? So because this is a DC generator, what makes us say it's a DC generator is this component. Okay, I'm gonna color it red. Okay, okay, and then we've got the other one there. We'll color it red just to show the similarity between those two. So these are called the split rings commutators, or we call them the commutators. So what these commutators do, they also give us an indication of what type of a generator it is, right? So because this one consists of the split rings, so if I draw the split rings, I can draw them like this. As you can see, these are two C's that are facing each other. So we call it a double C for direct current generator, right? So the current that is generated from this a DC generator is actually current that moves in the same direction outside this coil. So simply means that the graph of direct current versus time is like this. So this is half 10, then this is complete revolution, because this is 0, okay, that's 90 degrees, that's 180, okay, that's 270 degrees, and then that's what 360. So this is a typical example of a DC generator output, right? Okay. Now we also have motors. Okay, electric motors, they operate based on the principle that we call the motor effect, right? So a motor uses electrical energy to produce mechanical energy, or it converts electrical energy, right? Electrical energy, and converts it to what? To mechanical. So the output of a motor, be it an AC or DC, is that you must supply electrical energy in the form of alternating current or DC current, then it produces movement. So hence that conversion. So if I can go back to the generators, a generator will convert mechanical energy, because we have to move the conductor. Okay, this mechanical energy is converted to what? To electrical energy. That's why the light bulb glows, right? Okay. Right. So the motor effect tells us that if we supply current to a conductor, let's say there's current there, around that current carrying conductor, there is a magnetic field. Right. So if we take a current carrying conductor and subject it to a magnetic field and put it in another magnetic field due to the magnet, what will happen? Let's say we've got a north pole, a south pole here, right, of a magnet. Okay, that's south. And then let's say, for argument's sake, we've got the north pole this side, right? That's the north. So between these poles, there exists what we call a magnetic field, right? I'll use a different color. So this is the direction of the field, north to south, north to south, north to south, just like that. Okay, that's the direction of the field. Then what are we saying? We are saying that okay, I'll change the color there so that okay. Okay, I'll go there to the now. Let me go back. Okay, I'll change that color back to red. Right, there we are. And then if this current carrying conductor, the one that's red in color, it's got current in it, and then we subject it to a magnetic field, it will experience a force. The reason why it experiences a force is because it has got its own magnetic field. Then that movement of the coil or the conductor placed in a magnetic field is what we call the motor effect. This is the basis of the functioning of the motor. And now we know that motors drive, in South Africa at least, they drive on the left-hand side. So we use the Fleming's left-hand rule. It's still the force, the direction of the field, and then this is the direction of current, right? Whether it's AC or DC, right? And then there are two types of motors, AC and DC. Okay, we've mentioned that. Let's look at a DC motor as a practical example. Why do we call it a direct current motor? First of all, for us to say this simplified diagram represents a motor. first of all, we have got the direct current source. So the power source, okay, power source as in electrical power. So this battery does work in ensuring that there is current in the conductor there, which is placed in a magnetic field. So this is a typical example of a DC motor. Why are we saying it's a DC motor? Because we are seeing a DC source, right? So this is positive terminal, negative terminal. So current moves from the positive terminal to the negative terminal, just like that, by convention. Okay. Now, let's look at the components of a DC motor. We've got what is called an armature, okay, which consists of the coil, which is a conducting material, and usually it's copper. Why copper wire? Because copper is a good electrical conductor, right? It also has got the split rings. So these are the split rings, the double C that we spoke of. So they look like this diagrammatically. Okay, so then there you have that. Okay, so the moment you see a double C and there's a power source, it's a DC motor, right? And then there are carbon brushes. These carbon brushes, carbon is an electrical conductor. I'm going to color it red. These are carbon brushes that are actually fixed. Carbon brushes don't move. So the commutators, they move with the coil or the armature, okay? So this is the coil, right? And then we've got two magnets, the north and the south. So the direction of the field in this case is north to south, like that. So this coil has been subjected to a magnetic field, while the coil in itself, it is a current carrying conductor, right? So the split ring commutator, this is the double C, the split ring, okay? Commutator. So if you commute, you move back and forth. So a commutator in a DC motor, it reverses the direction of current every half revolution. A half revolution is 180 degrees 10, okay? Thus enabling the coil to rotate in the same direction. So the output of the DC motor is that we apply DC source, DC current, so that there's a current carrying conductor. We take that current carrying conductor, we place it in a magnetic field. Then in a magnetic field, it experiences a force. So the split ring commutator ensures that the rotation of the coil is in the same direction. Okay, that's the role of the split ring commutators. So think about, let's say a microwave oven. Okay, it has got a motor inside. So that motor, what it does, it rotates in one direction. Okay, because we supply in that case AC, because we plug it onto the AC mains supplies in our homes, schools, you name it. So we'll talk about also the practical applications of each of these, what you call the electrical machines, right? Now let's look at a typical example of an AC motor, right? Okay, the AC motor consists of the slip rings. Okay, now the slip rings are also fixed. They are different from the split rings in the sense that there's two of them, just like the split rings. However, what they do, they ensure that the current that is produced in this, what you call in this in this motor. So the current that is put in allows it to actually rotate in the same direction throughout. So there is a magnetic field there that exists. The direction of the field is north to south. And then this is plugged onto a DC source. So what it does, it allows us to actually output the mechanical energy. So where do we use these AC motors? Think about the electric drill that we use for DIY. Okay, the washing machines at home, the mixers, the small drill that the dentist uses has got an AC motor inside. Even the electric fan that actually spins and cools the room. So it has got what you call an AC motor because the source of current in the coil is alternating current, right? Okay, now let's look at the differences and similarities between these two electrical machines. Direct current. Why are we saying direct current? Because both of them has got the split ring commutators. Okay, so there's two segments of the split ring commutators. So on the left, we've got the motor. Okay, this is the DC motor. There is the battery. So this is the DC source. So the current flows in one direction. Okay, that's the direction of current, right? And then if that's the direction of current, and then we want to know what is happening in terms of the the current there. What's exactly happening is that in the coil or in the armature. So the armature in this case is the coil, right? And then the direction of the field is from the north to the south. There is B. And remember, B stands for the direction of the field, right? So if this is turning, let's say for argument's sake, it's turning anti-clockwise. This is anti-clockwise. This is clockwise rather, okay? And then that's anti-clockwise, okay? So just take note of the two directions there. So what the motor does, we supply DC energy from the DC source, and then it rotates in that magnetic field. Okay, that's one. So this is one difference between a DC motor and a DC generator. And then, but both of them have got the split ring commutators. All right. What is happening here is that the field is from north to south. Okay. So when we talk about the magnetic flux, we're actually talking about the density of those field lines. So how fast the conductor cuts across that magnetic field determines the amount of induced EMF. Hence, this is the graph of voltage output. Right. Okay. And then the Fleming's rules we apply for motors, we use the left-hand rule, and then for generators, we use the right-hand rule. So this is the right-hand rule. Okay. Okay, the right-hand rule. And then this is the left-hand rule. Okay, right. So left hand is for motors. Okay, and then right hand rule is for what? For generators. Okay, and I will look at the differences and similarities between the two types of machines. Right, here is what we are talking about. Let's talk about this. This is a very, very important slide in terms of the differences between a motor and a generator, be it AC or DC. Matters less. Let's look at each one of them at a time and then try to emphasize what is important, right? And then we know that then electric motor, it converts electrical energy to mechanical energy. So it's either we connect an electric motor to an AC source, then that's an AC motor, or we connect it to a DC source, then that's a DC source. In both cases, the rotation or the movement of the coil in the magnetic field is the output, while the opposite is true. For an electric generator, we have got mechanical energy converted to electrical energy. So first we have to move the conductor or the magnet, doesn't matter. We have to move, in often cases, we actually move the conductor in a magnetic field. So the movement of the conductor is kinetic energy, which is a form of mechanical energy, right? So if you move a conductor in a magnetic field, the output it produces electrical energy. That's why a generator, in the case of load shedding, what do? You switch on a generator so that you can turn that mechanical energy, of course, with a little bit of fuel, be diesel or petrol, to produce electrical energy, okay, which is an alternative source of energy. So that's very, very important, okay? And then a motor has got the split rings in the motor. They reverse the current. The split rings, they ensure that we've got what we call the DC output. Okay, so the split are this double C. Whether in a motor or in a generator, the double C is for direct current. So if there is a direct current source, it's an electric motor. Okay, so you'll see by the terminals. So this is a DC where we've got a positive and negative. So if it's connected to a DC source, that motor is a DC motor, right? And then AC replaces the commutator. Okay, so what the commutator does, is the alternating current is the current that reverses its direction every half cycle. So the example that we had with the alternating current is this one. Okay, right. This is 180. The current is flowing in one direction, 180, which is half the revolution, and then that's 360, right? So every half turn, current changes direction. So 180 degrees is in the positive direction. The last 180 towards 360 is in the opposite direction. That's what we mean when we're saying that the output current in the AC is actually alternating current, right? Okay. Now, the force is strengthened by, if we use stronger magnets, more turns in the rotor or coil, okay? And then we use greater potential difference, then we can have a greater output in terms of the electric motor. So similarly, with a generator, a stronger magnetic field will induce greater EMF, okay? More turns in the coil will induce more EMF. The greater the speed of rotation will also induce more EMF. Take note, on this the side of strengthening, the force is the output. This is the rotation or movement, which is the mechanical energy. This is the mechanical energy, while this one is the current, which is the electrical energy. Right. I hope that makes sense. Right. So this is one of the most important concepts that I wanted us to actually discuss. So what we're going to do now, we'll take a short breather, then we'll do a worked example, try and see how we apply all these items that we've discussed up to thus far. Now we'll take a 5 minutes break. Coming back, then we'll try and look at those worked example. Let's take a breather for now. grade 12s. We're still on our live broadcast session for physical sciences. This is your section on, we're talking about electrodynamics, which is electromagnetism, physics paper 1, which is of electricity and magnetism. Right. So before we went for the 5 minutes break, what we did, we also took a discussion on, the principle that underpins the functioning of generators, which is the Faraday's law of electromagnetic induction. And we also went on to explain the motor effect. We are also able to distinguish between an AC generator and a DC generator. Furthermore, we can also show differences between an AC motor as well as a DC motor. So let's look at the practical example of how questions will actually be assessed come end of the year or during the trial, and you need to prepare, at this level of, difficulty and cognition. Right. So the simplified diagram below represents two electrical machines, A and B. So these are machines. Okay. Classify the above electrical machines into DC motor and generator. All right. So both of them are DC. Why are we saying both of them are DC? Let's study the first one on the right. The one on the right, look at that component. This is a split ring. Okay. And then the output, the input here, as you spin that handle. So this is an input of mechanical energy. Okay. And then the output is electrical energy. So in this case, this is a DC generator. So A is a DC generator, right? Okay, because of the split ring commutators. Also, the input is mechanical energy. While machine B, it's a motor. Why are we saying it's a motor? That's a DC source. Okay, so it means this is a current carrying conductor. That's the direction of current. Okay, then B is a DC motor. Why also DC? Because of the split ring commutators. Right? So that's another split ring commutator. Right? So this is a DC motor. Okay. Now the difference is that for A, we put mechanical energy. Here, this is electrical energy source. Okay. That's electrical energy. And what do we know already, grade 12? We know that a motor converts electrical energy into mechanical energy. So the output in this case is the rotation, right? So the output is the rotation, while on the machine A, input is mechanical energy, output is electrical energy. Okay. All right. That's straightforward. So give a reason for each case. So DC is a motor because of the energy source, right? Okay. Here is electrical energy output. Okay, so that's how we distinguish. So it's 4 marks. Why? For saying A is a DC generator is a mark. Stating the reason is another mark. For saying B is a DC motor is a mark. To say that there is an energy source as a reason to support your choice is another mark, which gives you the total of 4 marks. Okay, then let's move on to the next question. What? So pay attention to the action words. The word what is straightforward. You answer that question directly. It's like a question says to you, what is your name? You just state your name without any explanations or illustrations whatsoever. It's a direct question. So pay careful attention to the words that are used to phrase the question. What type of generator, AC or DC, is represented in the simplified diagram above? So this is more like a reputation. The generator that we have is a DC generator. Why? Because of the split rings. because of the split ring commutators. Okay, so the structural differences between a DC a generator and an AC generator is that a DC generator, let's just go back there. A DC generator has got split rings, okay, split the double C, okay, and then an AC generator has got the slip rings. So these are the structural differences. This is slip, the solid ones, okay, these are the slip rings, okay. So this is how you distinguish between those two, right? And then for identifying that A is a DC and stating a reason is a mark for each. Okay, name the principle on which generators work. Pay attention to the marker location. When they say name, it's a straightforward and direct. What principle did we use to explain the functioning of the generator? We even went to the extent of also discussing the factors that will affect the magnitude of the induced EMF. So we call this the Faraday's law of electromagnetic induction. Okay, so the principle is Faraday's law of electromagnetic induction. Okay, and with this question, it's either you know or you don't, because it's 1 mark. You don't explain that, you just remember it. So that's why we're saying, by all means, this is a very, very straightforward question, right? Now, which one of the graphs ROS represent the voltage output of the generator identified in 9.2, right? I didn't put the graph deliberately. And there is only one generator here, okay? The generator that we have in this case is electrical machine A. So if it was referring to A, then we'll have a DC generator, okay? DC generator output is direct current, which means is even the output voltage is in one direction. Okay, so this is one complete revolution, 1.5, and then 2 revolutions. So this is the peak that is actually achieved, which is the maximum induced EMF. So this is EMF or volt in volts, and then that's time in seconds. All right. Okay. And then the multiple choice, I think even before we went for break, we agreed that the multiple choice is by far one of the very, very important skills that one needs to actually gain and be comfortable with, because section A contains 20 marks of the multiple choice. So it is for that reason that if you want to get a distinction, you need to get a minimum of 16 out of 20 in section A. So that goes without saying that it will be very key for us to also, expose ourselves to as much multiple choice practice as we possibly can. Right. So I'm gonna give you 2 minutes just to try this multiple choice. Remember, read the question, the problem statement with an intention to understand. Therefore, follow up with eliminating the 2 distractors, and then we are left with 2, and then choose the correct answer. So your 2 minutes starts from now. Grade 12, I will ask you now to stop so that we can take a discussion on the multiple choice. I also want you to use this opportunity to appreciate that multiple choice questions, much as we are given options from which we are supposed to choose the correct answer, it's not always, a hit and run type of a situation. You must read the question, understand it, uh, identify the distractors, eliminate, and then come up with the correct answer. So at your first glance, when you see what could be possibly the correct answer, what you may think is the correct answer, it doesn't mean that you don't have to look at the other options as well. So that's a technique that one must actually, develop insofar as multiple choice is concerned. So an electric device that uses electrical energy to produce mechanical energy. Now, first of all, the energy conversion that is highlighted here. Okay, because energy cannot be created or destroyed, but it can be transformed from one form to another. Now, we're saying electrical, okay, to mechanical. Okay, this is what this machine does. Now, let's look at the options. An electric motor, okay, there might be some truth in that, okay, because we know that a motor converts electrical energy to mechanical energy. An alternator, right? An alternator is a generator. Okay. Now we talk about applications of generators or the uses, right? So the word application speaks about uses in automobiles or in cars. Okay, automobile, just automobile. Okay, or in cars. What an alternator does, it charges the battery while the car is in or the engine is running. Okay, so the running of the energy of the engine is mechanical energy, which charges the alternator uses to charge the battery. That's why you can play music in a car for a long period of time, but once it's used up, it's recommended that you start the engine so that it runs. While it runs, it's mechanical energy that is being converted to stored electrical energy. So an alternator is a generator in vehicles, right? A dynamo is another form of a generator. It's a fancy name for a generator that is used in bicycles. So as you cycle, the bicycle doesn't have a battery. Okay, you use mechanical energy to cycle. As the wheel is rotating, the cap of the dynamo is in contact with the wheel. Then the light or the lamp of the bicycle goes on. Okay, so a dynamo is a generator. Okay, and the generator is a generator. Goes without saying. So all these three, B, C, and D options talk about generator. The only motor that we have in this case is the electric motor. So A is the correct answer. Right. So according to this question, we don't want a generator. We don't want a generator. We're only looking for a motor. So for all this trouble is 2 marks. And there are no part marks in multiple choice because it's either the option is correct or not. All right. Okay, let's look at this individual activity. I'm going to give you about 5 minutes or so because it's a very, very straightforward question which basically talks about a recall. It talks about a simplified sketch of a generator. So we're told that this is a generator, okay? So it has everything to do with the generator, okay? Or with the Faraday's law, all right? We're given the direction of rotation of the coil in the magnetic field there. We're given the annotations or the labels for the components. I'll give you 5 minutes to try. This is an individual activity, so I want you to try it alone. Then when we do the feedback, you get an opportunity to see where you might have gone wrong so that you don't commit the same mistake again. Your 5 minutes starts from now. Welcome back, grade 12. I'll ask you now to stop. Let's try and reflect and see if we are able to apply the knowledge that we have gained insofar as this session is concerned. Now, we are told that this is a generator, and for some reason, we are given the direction of rotation there. The direction of rotation is counter or anti-clockwise. So this is anti-clockwise, right? This is anti-clockwise rotation. The direction of the field is north to south, right? Okay. And then we're told that it rotates anti-clockwise. So if it rotates anti-clockwise, this side of the coil is going down, this side is going upwards, all right? Then we're told that the north and the south poles of the magnet remain unchanged. So these are fixed magnets, okay? We're interested in the north and the south, this side. That's why we say the direction is from left to right. And then if the coil is rotated in the direction as shown in the sketch, will the induced current flow in the direction as indicated? Answer only yes or no. That's why it's 1 mark. So we have to apply for generators. Okay, we apply generators. We apply Fleming's right-hand rule, right? All right, we apply Fleming's right-hand rule. So if we are going to use the Fleming's right-hand rule, we will hold our 3 fingers like this in perpendicular to each other. So that's the direction of the force. Okay, that's the direction of the field, north to south. That's the direction of current. Okay, let me go back. Okay, just a moment. Okay, now if that's the case, we are saying it's north to south, and then the direction of the field is north to south. There is my north to south. So the side that's closer to the north pole is going down. That's the direction of the force, and then the finger is facing towards me. It means this side, the current must be this way. Okay, that's the direction of the current, and the other side must be that way. So it's a big no. So the direction of the current has been opposed there. So that's why it's 1 mark. For all that trouble of using the Fleming's right-hand rule, 1 mark for that. Come to think of it. Okay. And then is the output AC or DC? Now we have to pay attention to the structural differences. We said if there are slip rings, it's definitely going to be an AC generator. Okay. So because of the slip rings. Okay, so the slip rings suggest that it's an AC generator, right? Okay, straightforward. What would happen to the output voltage if the coil is rotated faster? Okay, now this speaks to the factors that affect the magnitude of induced EMF. So they're asking us what will happen to the voltage. So the voltage, if we rotate faster, faster is speed. The greater the speed, the greater the magnitude of induced EMF, right? So here it's going to increase, okay? So increasing the speed will increase the amount of output voltage, which is the induced EMF, right? And then 9.4, what is the position of the coil relative to the magnetic field when the output voltage is maximum? I want you to pay careful attention to this one. If the coil is lying like that in a magnetic field, and the magnetic field doesn't change because it's filled, it's a field, okay, the magnets are filled, fixed rather, okay? So if they're arranged in this way, they are actually parallel to each other. Now, the coil, as it turns, it actually moves perpendicular and cuts across the magnetic field. So the position is parallel. The movement is perpendicular. Okay, I'll repeat that. The field which is fixed because the magnets just there, they are permanent magnets, and we're told that the north remains there, the south remains there. So the field, this invisible magnetic field, is from north to south in that horizontal plane. And then again, we've got the coil lying in the same plane like that. So in terms of position, they are parallel. While the coil rotates, these edges of the coil cut across the magnetic field and induces a maximum EMF. So they must be parallel to each other. Now, this is maximum. At position, this maximum. Okay, when they are perpendicular, it's zero EMF. I'll explain why. EMF induced will be zero when the field is like this, the magnetic field, and the coil is in this position. Okay, when the coil is perpendicular like this, it means it is moving parallel. So this part moves that way, this one moves that way. As a result, the movement is parallel in a perpendicular position. So for the coil to induce the maximum EMF, the coil and the field must be lying parallel to each other and moving perpendicular. So movement and position are always opposite. Okay, when it's parallel, the movement is perpendicular. When the coil is lying perpendicular, the movement is parallel. And what we know, if movement is parallel and two parallel lines never meet, it means that there is no interaction between the coil and the magnetic field. Hence, we induce zero EMF and zero current. Right? Okay. And then one last one before I give you a homework activity. We'll do this one together just to try and consolidate, because these are basically straightforward type of questions. It says here the diagram below shows a simple generator. Okay. Is this an AC or a DC generator? Okay, if we say this one is an AC because of the slip rings, then this one is a DC generator because of the split ring commutators. There is the double C there, right? So this is a DC generator. Give a reason for your answer. The reason why it comprises of the split ring commutators. Okay. Okay. Now, write down the name of part A. Okay. Part A is the coil. Okay. Part A is the coil, which is the armature. So if you say it's a coil, this is a copper wire, which is a strong electrical conductor. Okay. So the more turns in the coil we have, the greater the magnitude of induced EMF. And then last but not least, describe the energy conversion, because energy cannot be created or destroyed, but can be converted from one form to another. So this generator converts mechanical energy, okay, not mechanical, but mechanical energy into electrical energy, because the generator produces electricity after all, right? Okay, so these are direct, straightforward questions that we must be able to pick up marks. And historically, learners have done very well in this section. And then the next one is a homework activity that you'll do with your teacher, and practice this. So our follow-up lesson, so the homework activity will actually be these two questions, right, which are very, very straightforward, right? Right. Having said that, I just want to say electrodynamics is a topic that's somewhat abstract in a way, but once you get the hang of it, everything is just straightforward because it involves basic recall. This is as far as the first part of electrodynamics, which speaks to motors and generators. The next week, when we meet at the same time for our live session, we'll be looking at alternating current, where we'll look at purely resistive circuits. We'll look at alternating current calculations, the data sheet, which is the last part of electrodynamics. Right. So with that said, for myself, Temba Ngube is cheers and bye-bye.